So, hello everyone, we are back to our class again, and now gradually we are entering into the actual applications, real life applications of whatever you have learned in these days. We learned all the theories, starting from the very basics, we have derived those equations. Now it is our time to apply those and try to see whatever you have learned through complex mathematics or whatever you say, how to apply them in actual problems. So, the whole purpose of this course is basically to bring the knowledge from textbook to the actual application area. Just limiting us to the textbook, it is of no worth. So, whatever I will be telling now onward, it is basically we will enter into the real life world, actual problems, actual processing area, where we will be now onward applying our knowledge to extract the information about practical systems. So, in doing so, there are two ways. One is numerical simulation using those equations, whatever we have learned, and the other one is making the devices and entering into the process area. So, this numerical simulation nowadays is an indispensable way to understand the systems, because infinite number of designs are possible for any system. Out of them, which one is the right one, an experienced person can tell a limited number of set. But why I am telling that limited number of sets, because even though he makes the list a short one, it will also include variety of possibilities. Out of them, if you want to choose the best possible one without making the device actually, then numerical simulation and is one of the most most elegant technique to do that, to save money as well as time. So, we are now entering into that, and what we have seen that in plasma, starting from the kinetic theory model, we have reached to the plasma fluid model, which was basically having a set of conservation equations, and depending on the type of model what we are using, whether it is equilibrium model or non-equilibrium model, a set of conservation equations will be there. Now, we are very lucky that all these conservation equations come in the form of a generic type of equation. So, this is the generic type of equation. Of course, this is for your steady state system behavior where time is not there. So, what it contains? A convective term, a diffusive term, and a source term. So, whether it is mass conservation equation or axial momentum conservation equation or radial momentum conservation equation or the energy equation or the your particle conservation equation, all of them are having a generic form of this type. Only thing is that this phi, gamma phi, s phi, these quantities just vary. So, that is a very nice thing, because we can now make a mathematical framework which will solve only a single equation. So, the framework will be for solving a single equation, only will change these parameters so that it can give us information about different things like say velocity, like temperature, like potential, like number density, all these things will be getting out of that, and I explain in detail these equations what they are. Now, it is our time to apply this equation to actual real life problem to see how we can extract information about the system. So, this course, that theory and applications in cold and thermal plasma, is essentially making you fit for this real world. Maybe, and rather than not maybe, it is for sure you will need to learn a lot more than what I will be telling here. This course is only to give you a route map about how to proceed to solve a real life problem. Now in that route map there will be number of points where you will require to learn a lot, do study a lot to make it actually implementable in your system. Now, so for those things you need to learn, and I can say you that I am still learning every day something or other in this. So the more you study, more you learn about the system, the more you get experience on how to handle different difficulties in that. So I just give you a flavor and a route map for how to use this knowledge of say theory in plasma in actual application area. So I start with, so the essentially the thing was that we will be going for a fluid dynamic code which will solve the mass conservation equation, momentum conservation equation, species conservation equation, current conservation equation and energy equation. And to solve that what we need, they are the thermodynamic and transport properties. Thermodynamic and transport properties on the other hand needs input about the species temperature and species densities. Once you give them, then they do have a library of this collision integral and collision cross sections which have been gathered from lots of other theoretical studies and framework. When you feed that to the property code, then you get the transport and thermodynamic properties. You feed them to the fluid dynamic code, because as I told you earlier that the coefficients like the viscosity, like electrical conductivity, like thermal conductivity, like diffusion coefficients, all these basically are transport properties, and these properties are basically supplied by this property code. So whenever you are going to solve a plasma problem, although they are solving the essentially the Navier-Stokes equations with modified coefficients and source terms, but they are different from ordinary fluid like water. This is because their property are highly nonlinear with respect to temperature, and as the temperature varies, the properties varies. Unless and until you are able to give right property for right at a given temperature, it will never ever give you any solution which is close to the practical one. So the importance of the fluid dynamic code and importance of the property code, they are equal, or I will say that importance of the property code is bit more, because this part is usually very complex, and still the properties codes are getting being improved, so that you can get better and better results, because this depend, there are a number of uncertainties on which they depend, the kind of potential through which they interact, and the collision cross sections and collision integrals, they are improving day by day, and so there are scopes of improvement for this property code. Otherwise also, see, most of you may have already graduated, and you have learned a lot in your courses in physics or engineering, but still if I ask you how to calculate the say thermal conductivity of the air in this room, then you may not be answer very straightforward, because we really do not come across a course which allow you to find the thermodynamic properties or transport properties of the gases. Some of them we have learned, of course, everything is dependent on basics. Basics we know, but how to use those basics to actually get the properties, it is bit unknown, or we are not very much familiar with that. So I will give you a route map of how to get those things, this property code, and how to enter into this fluid dynamic code, and how they work together, how the solution looks like, how the solutions proceed. So all these things will come in this course. So first, the thermodynamic and transport properties. The thermodynamic properties, I have already told in the beginning classes. Once you solve the Sa ionization equation, this one, then you can get the thermodynamic properties rather easily using the concepts of the thermodynamics and statistical mechanics. So all these equations basically as I elaborated in the initial classes. Now comes the transport properties. So for transport properties, every system is different, because it depends on the interaction among the species, and that interaction depends on what kind of species present in that system. So, just to elaborate the mechanism, I have chosen here in this a specific model of air roughly, because I have considered nitrogen and oxygen similar to what is there in the air. Of course, air is containing other species, but this you can to be technically correct, you say that this is a system of N2 and O2 species. Okay. Now, whenever you are giving an N2 O2 species at normal temperature, well, they will be in the molecular state, right? But as you raise the temperature, what will happen? This N2 will break to N, O2 will break to O. Then you increase further, then N will be ionized, O will be ionized. So, with increase in temperature further, you will get singly ionized, double ionized, triply ionized species. And now you see that all of them will interact with all of them, and they are open to react with each other, because N and O, when they react at very high temperature, they easily form NO, and you know that NO can give you molecular ions as well. Now, similarly, your oxygen also can give you molecular ion. So, the number of species for a realistic model that should be considered in this case, I have shown here that they are 17 in number. So, what is that? O2, O2 plus, O2 minus, O plus, then O double plus, N2, N2 plus, N plus, N double plus. Like that, I have considered 17 species. Now, each of the 17 species in this first row, they are interacting with each of them in the first column. So, O2, O2 will interact, O2, O2 plus will interact, and that way you are seeing that 17 into 17, that 289 types of collisions are present over here. Now, you know that when A interacts with B and B interacts with A, if you consider them as the similar, then what is happening, that only the upper diagonal term, upper diagonal elements, not diagonal, upper part of this diagonal, whatever the elements are there, that colored zone, if you consider them, then that is fine, and you can say that the interaction AB is same as the interaction BA. So, considering only this much interactions is sufficient. So, this reduces your complexity by half. Okay. So, and that is quite realistic also. Now, the issue is that the interaction is not of the same type. So, it may be neutral interaction, ion neutral interaction, ion resonant interaction or non-resonant interaction, then charge interaction, then electron neutral interaction. So, these are different kind of interaction, and for each interaction there is a different kind of interaction potential. So, for any practical system, you have to first understand what are the species present there. How will you know the species? From the Sa ionization equation you can get to know about the species. Once you know which species are present there, then you have to first search what type of interaction they are doing. And in this diagram you can see that this yellow zone is maximum. So, what is yellow zone? This is the charged interaction, and it is natural because you are considering a plasma which is an ionized medium. So, it is natural that charged interaction will be the maximum one. So, that is what you are seeing over here. Other than that, what I have told you, that ion neutral and neutron neutral interactions are also there. This is because when you are staying at low temperature, then there is a possibility that neutral will be present there, even molecule can also be present there. And when you are actually forming the plasma, you are starting from very low temperature like room temperature. So, that time whatever the species present there will be molecule, not ionized. So, if you are considering all this starting from room temperature to a very high temperature in an integrated manner, you cannot avoid considering the collisions among the neutrals as well. Okay. So, that is why all these interactions and all these species are equally important. So, now I will come to the aspects of finding the transport properties. So, usually this the transport coefficients are determined using the first order perturbation technique of Chapman and Enskog. Okay. So, if you want to know more about this method, then that is a huge volume Hisfielder, Curtis and Bird, they have written a big volume on these aspects, and you can go there and you can read about what and how these properties are coming from the Chapman-Enskog approach. So basically, in this method, what is being done, the transport coefficients are determined in the form of ratios of infinite determinants. Okay, the convergence of the ratios of the determinants is very rapid as you increase the number of rows and columns. So, that is the hope, because infinite determinants is meaningless as far as practical considerations are there. Now, the hope is that if you increase the number of rows and columns, they converge very fast. So, fairly accurate values of the transport properties can be obtained if you consider only few elements, few rows and columns in the determinants. So, that saves us, and the elements in the determinants are expressed in terms of combination of bracket integrals, which can be expressed in terms of this collision integrals omega ijls, whatever is there. So, I will tell you how they look, what is the exact form of the known things like thermal conductivity, electrical conductivity, viscosity. These terms we know, but when you are telling that this comes in the form of determinants or ratio of determinants, then how do they look? And if we want to increase the order of approximation, then how their behavior change, how the determinants change, whether it is easily doable and you can do it. So, I will tell you these are complex things, but actually really not that complex. I am sure that after finishing this class, you will be able to write the determinants on your own. Okay. So, we proceed. So, you know that collision integrals, if you want to calculate, you start with an interaction potential, then you calculate the deflection angle, gas kinetic cross sections, all these how they are to be calculated, I have just given in that explicitly. Then you get the collision cross section and collision integrals, they are interrelated. So, you can express this omega ls in terms of qls like this. So, it is doable. So, the first thing you need to know is the interaction potential to do the calculation of the collision integrals. So, now we assume that we will proceed through this route and we will be able to find the collision integrals. There are lots of literature where these collision integrals have been addressed for different interactions. So, we can get help from them, and we can save lots of our time because the work is already done. So, these collision integrals are sometimes expressed in some polynomial form, or so in some closed form they have given with some coefficients. So, it will be easier for us to generate those equations if we study the literature. So, anyway, this is the route, and what I am saying that many of the collision integrals are already calculated and available in literature. So, what you have to do, you have to go to literature and you have to find how they look. So, like that. Now, when you are coming for molecule atom or atom interaction, so they are some sort of neutral kind of interaction, and that is usually calculated under exponential repulsive potential like this, and this omega ij collision integrals can be expressed in this type of forms, where A1, A2, A4 and A5 are some coefficients which can be obtained from literature. Okay. So, they will be different for different molecules and different atoms. So, but anyway, the collision integrals can be expressed in this form, and this Tij is the reduced temperature which is expressed in this form when I and J are the interacting particles, Mi, Mj are their masses. So, if they are having different temperature, then their reduced temperature is like this, and the collision integral can be expressed in terms of this reduced temperature like this shown. Now, coming to the electron molecules. So, this type of interaction are charged neutral interaction. So, for that actually direct numerical integration of relevant momentum transfer cross section can give you those, and this type of interaction usually come in the form of the collision integral comes in the form of this type, where there are so many coefficients like C, A2, A3, then A7, A4, they are all there, and these values are available in literature. Okay. Now coming to the ion neutral cross section. So that was electron neutral and this is ion neutral. Again this is a charge neutral interaction, and usually these are calculated using polarizability model, in which the collision integrals assumed a closed form of this type. So this is rather easier to find out. You know that this is again the reduced temperature and expressed in this form, and this polarizability. So this you need to find out, and you can see that the polarizability for different species are like this. So the polarizability factor you have to put accordingly, then you will be getting the values. This alpha is the polarizability factor which has to be introduced here, and you see that different your molecules are and atoms are having different polarizability, which is quite expected. And if you calculate the reduced integral as a function of temperature, this is electron temperature, and you see that how do they look. Okay. So this is just to give you an impression that what forms these collision integrals take when you actually want to go for calculation of these collision integrals for different kinds of species, and in actual values how they vary. So these graphs you are giving some impression about how should they look, and these are the kind of expression they follow. Now coming to the charge-charged interaction. So earlier this was pretty complex, but now there is one model we have developed where you can express this collision integrals in very closed form like this one. So this cross section comes from the integral, as I have already told you that they are related. So once you know this parameter, for different kinds of species, then you can calculate the collision integral for charge-charge interaction very easily, and you know that because it is a plasma, most dominant interaction in plasma is the charge-charged interaction. Okay, so that's why this is very much important, and the finding finally the transport properties from these collision integrals. So there are different levels of approximation to get the values done. As I told you that as you increase the number and rows in the this transport coefficients, then you find that only few rows and columns if you consider, then also you are getting very accurate. But that is not the same for all kinds of transport properties. I have shown you here some transport properties which are giving pretty accurate values. Okay. So for viscosity, you know that only fast approximation is sufficient. For binary diffusion coefficient, again the first approximation is sufficient. But if you want to get really accurate values of the diffusion coefficients for heavy particles or thermal conductivity of the heavy particles, then you really need to go for the second approximation. And the collision integrals that will be required are just shown over here. And you know that thermal diffusion coefficients of electrons, if you want to calculate that, even second order approximation is not sufficient, you need to go for the third level of approximation. And similarly for electrical conductivity, you need to go for the third level of approximation, and you know that as you increase the level of approximation, you know the more number of collision integrals you require, and for that actually the calculation is a bit intensive, but anyway they are fairly doable, there is no issue in that. Now regarding the level of approximation, when I am saying, then you are definitely thinking what they are actually. So I have just given one example over here. So here what you are doing here, you are calculating the thermal conductivity. Okay. So when you are doing for the second order approximation, okay, then you are including these elements only in that, and these elements are expressed in terms of the collision integrals. And what is the exact functional relationship? For that you need to go to literature and you need to find how they are related with the they are basically algebraic expression in terms of the collision integral. So you will be able to find that. Now you just look into the terms. See, second order approximation I am trying to do, and what I have done, 0, 0, 0, 1, 1, 0 and 1, 1, that is sufficient, and I am doing the approximation. When I am going for third order approximation, you see that the matrix which was determined, which was 3 by 3, now it has increased to 4 by 4. And what you are including apart from the earlier one, you are including Q02. And here also you are coming to Q23, okay? Another row that has been included over here. So what you are getting, third order approximation is like this, third order one. And when you are going for fourth order, what you are finding here, then you are using 5 rows and 5 columns. So just looking at the form, I hope that you are able to understand that if you want to increase the order of approximation, how to change the determinants. You understand over here. So this is the determinant upper one, and you see that how the rows are changing, columns are changing when you are increasing the order of approximation. And these elements, their exact relationship with the collision integrals, they are available in literature. So now you know that how to increase the order of approximation. And I must tell you that, see, if you are working with the third order approximation and if you are working with the fourth order approximation, you will see that there is almost a negligible difference in the calculated values of this thermal conductivity. But if you are going for third and second order, then you will see that there is a significant difference in the thermal conductivity, because you see that is why you are going for this third order approximation for thermal conductivity of electrons. So this is the relationship mostly we are using for calculating the third order thermal conductivity, because this increases the accuracy, at the same time it reduces the your computational load. So that is how we are going for this third order approximation when you are going for this thermal conductivity calculation. Now I will tell you that thermal conductivity of electrons, how we are calculating. See, this is the third approximation and we are using this kind of relation. And similarly, for thermal conductivity heavy species, we are going for second order approximation and we are calculating like this, okay. Now, this last one actually, this was for electrons or this is for heavy species basically, yeah. So usually we are doing thermal conductivity of electrons using your third order approximation, and for heavy species we are using second order approximation. So just now whatever you have seen, this is we are using for electrons, and this one we are using for heavy species, second order approximation. Now coming to the electrical conductivity, we are using third order approximation, and the viscosity first order approximation, but that expression is pretty complex, okay. Now I was telling always that the elements are expressed in terms of the collision integrals, and there is some algebraic relationship between these elements and the collision integrals. And how do they look? That has been just for one example, that how the relationship may be. So they look like this, okay. Just this is for the elements of viscosity. I have just shown over here. So this is like that, and as you go for these other elements like Q01, Q02 or Q21, Q22, so they will look a bit more complex, but anyway they are algebraic expressions and completely manageable. So finally what you get, actually I have just given one example that how the thermal conductivity, viscosity, electrical conductivity and volumetric collision frequency varies in such cases. As I told you that they are appearing in the coefficients of the your fluid dynamic equations, and you can see here that if you are going from equilibrium to non-equilibrium model, they are varying a lot, yeah. So how they are varying, you can have an idea. So this shows you how important it is to include the non-equilibrium in your modeling results, okay. So similarly you can go for the other things. See, this is reactive thermal conductivity, thermal diffusion coefficients, and reactive thermal conductivity of heavy particles, and this one is thermodynamic property, not the transport properties. Okay. So, just I wanted to show that how strongly they depend on the non-equilibrium nature of the system. So, when your system is some region it is in equilibrium, some region it is in non-equilibrium, better to go for the non-equilibrium model which encompasses both equilibrium and non-equilibrium. Okay. So, that is what the advanced modeling nowadays we are doing to get the actual behavior of the system, to understand the behavior of systems. So, with this actually I stop here, so you know that how the properties in the property code can be computed using the framework of standard physics. Okay. So, I stop here, and in the next class I will show you how the simulation actually goes. Okay. So, see you in the next class.